So the best way to understand the Lagrangian description of a flow is to think like a duck, or more specifically, to think like the rubber duck in our experiments. So remember, this duck is floating happily down a flume in our laboratory. It's been carried by the fluid around it, but the lab is completely stationary. What we're going to do to describe our Lagrangian ducky is to consider the ducky to be a particle in the fluid which moves at the rate of the fluid. That means that the particle, or in this case the duck, carries all its properties with it, including, say, its temperature, or its density, or its materials. It also carries its momentum with it. So to understand this a little bit better, let's put ourselves in the point of view of the duck and call this the Lagrangian frame. In the Lagrangian frame, we're going to denote time by the variable tau, noting that tau is just equal to the regular t that we use for time, but we're also going to identify each fluid parcel by a label, A. Think of this as we're going to give each duck a name. Then we can write the position of each particle as x, the position in the horizontal, of A, tau. We could generalize this to 3 dimensions if we wanted by making x and A vectors, but we won't do that for now. The advantage of going this direction is that in our Lagrangian frame we can now write u, the velocity, in the x direction, which is also a function of A and tau, to be simply the time rate of change of x, or partial dx d tau. In this case we use the partial differential because x is a function of both A and tau, but we're holding A constant, meaning we're sitting on one particular parcel while we take our time derivative. Okay, so now let's take our arbitrary function. We used to call this arbitrary function f of x and t. Now I'm going to write it in the Lagrangian description as f of A, tau. Then if we take the time derivative of f in the Lagrangian system and we convert it to the Eulerian system, we write df d tau by the chain rule is equal to df dt dt d tau plus df dx dx d tau. There's a couple of immediate simplifications here. Firstly, we said that t is just the same as tau, so dt d tau is just 1. That means our first term here is just df dt. The second term, we know that dx d tau is simply the velocity, u, so we can write the second term as u times df dx. In other words, df d tau, the time rate of change in the Lagrangian description, is equal to a local rate of change in the Eulerian system plus whatever is carried or vectored by the velocity field. We're going to write this as a capital df dt, which is something we define in fluid mechanics as the substantive derivative, or often called the total time derivative. Note that in 3 dimensions we can write the total time derivative, df dt, is equal to the local rate of change, partial df dt, plus vector u dot with the gradient of f, and I can show you that in more detail later. Initially though, we're just going to use the total time derivative in its one-dimensional form, and in the next video I'm going to show you how to use that to derive a very, very simple equation of motion for a fluid.